Thank you very much, Anna Maria. Thank you, Klaus, Clemens, Mariana, for organizing this wonderful conference and for inviting me to it. Thanks, June, for the amazing first talk, which is a great, I think, lead-in, although also hard to follow, I have to say. But yeah, as Anna Maria said, I'm going to tell you a little bit about our work now at UC Berkeley. Much of this experimental work was done at the University of Wisconsin-Madison before I moved to UC Berkeley, about testing relativity in the lab with a miniature clock network. Also, much of this work was sort of inspired by and was only possible because of everything I learned working with June in June's lab and inspired by a lot of the ideas that we had while working with June. But before I start, I do want to say I'm also an Israeli citizen. My mom is from Israel. So this past weekend has been quite upsetting and difficult for me. And I also have a lot of friends and colleagues. I think we all have scientific colleagues in Israel. So I've been in touch with some of them. Sorry, my clickers. And so Ofer Furstenberg, who's one of our colleagues in AMO at Weizmann, asked me to actually share this message. Basically, all I want to say is it's very weird to be here with all of you and to be in this beautiful place and also to see so much suffering happening in Israel and Ukraine and everywhere in the world. And I think that science is a luxury of peace. But also it can be hopefully a tool for peace. And so I think it's great to be here fostering international collaboration. And I hope that, coming out of this in the end, we can all just be advocates for peace and try to work towards a time when no one has to be living in fear for their lives and their families. Okay, so having started off with that message, let me sort of shift over to science. Okay, so why do tests of relativity in the lab? So this talk is about the tests we've been trying to do of relativity in the lab. And one reason I think is just because, we have these two incredibly successful theories. We have the theory of general relativity and we have the theory of quantum mechanics. And I would say these are the two of the most successful theories, in all of science, right? They've passed every single test that we can throw at either of these theories with flying colors. I mean, recently with LIGO, we now directly observe gravitational waves from cataclysmic events that are truly beyond anything that I think the human mind can comprehend. Black holes, tens of the masses of our sun, merging with each other and emanating more energy in the form of gravitational waves than all of the stars in the universe combined are emanating through light. And yet everything is still consistent with the predictions of the theory of general relativity. And at the same time, of course, we have quantum mechanics that governs, the structure of matter and that we're now using to make remarkable new technologies and devices. And we're doing these incredible many-body experiments that June was talking about. And again, everything that we see is consistent, but we don't have any way of merging these two theories. We don't know how to bring them together. And so first of all, that motivates just doing more tests of both of them and trying to push at them and prod at them and see if we can find any weaknesses. But I think it also motivates doing tests, as June already just talked about, at the interface between these two theories to the extent that that's possible. And so doing tests of relativity in the lab with quantum systems is, I think, a promising way to try to maybe hopefully find some ways to maybe bring these two theories together and reconcile them. Okay. And so I'll be talking about mostly, measuring gravity with these clocks and trying to see the effects of relativity. And at the heart of relativity is the Einstein equivalence principle, the idea that, the being in a gravitational potential is sort of equivalent to acceleration. And you can decompose that Einstein equivalence principle into these three kind of more fundamental symmetries. We can have tests of local position invariance, tests of local Lorentz invariance, and then tests of the weak equivalence principle. And all of these things have been tested quite well, as you can see here. But I'm going to focus today in my talk on doing this kind of tests of local position invariance. And as you can see from this plot, essentially all of the existing tests, with the exception of maybe the first one, which I'll talk about in a minute, are done primarily in rockets and spacecrafts and planes. Or they're of the form of these null redshift measurements, which I won't really talk about today. But I'm going to tell you about trying to do some of those same kinds of experiments that are being done in rockets and spacecrafts and planes in the lab. And in particular, the form of local position invariance test that I'm talking about is a test of the gravitational redshift, which we already heard about from June. The idea that either, you can think about it two ways, if you lift a clock up in a gravitational potential, it will tick faster than an otherwise identical lower clock. Or if you want to think about it as a photon climbs up out of that potential, its frequency shifts, right? And you get a gravitational redshift, which is why it's called a gravitational redshift. Of course, the first test and one of the very first tests of relativity, and I think definitely the first test of general relativity performed in the lab, was the beautiful Pound-Rebka experiment, which was done with Mossbauer spectroscopy at Harvard. And it's, I think, pretty amazing to think about doing this experiment already in the 1960s. But you know, one of the challenges with Mossbauer spectroscopy is that you have no idea what the actual frequency of the you know, Mossbauer radiation, the gamma rays that you're measuring, and it, you know, so it, and also if we look at this picture that I showed you, there were these kind of two different ways to think about the redshift. Either you can think about it as kind of the photon shifting, which is I think the way that Pound and Rebka framed their experiments. I think the original paper was titled something like observing the effective mass of the photon or weight of a photon or something like that. Or you can try to look for this clock shift, right? And it's natural to try to do these measurements with clocks. And so, so you can, you know, look at an atomic clock, which we already heard about from June, and I won't sort of introduce, and you can write down what the fundamental quantum limits, which we also heard about from June, are for the behavior, for the, you know, performance of that clock, purely from quantum projection noise. So just from the fact that we're comparing this radiation to atoms, and when we make a projective measurement of the atoms, they either are always in up or down, and so without using any of the fancy entangled states that June told us about, we can write down this fractional frequency instability from quantum projection noise and say, can we do this kind of experiment? Can we actually see these effects? And the answer is yes. So in the 1980s, this was done with hydrogen maser on a rocket. This was Gravity Probe A, and this is one of the more precise tests of the redshift that has ever been performed. And you can see that they got very good agreement with the expected effects. But then you can ask, well, I don't really want to put my clock on a rocket necessarily. That's challenging. Can we do some of these tests in the lab? And if you look at the performance of the very best microwave clocks that you can make, and you look at the size of the redshift is 1 × 10⁻16 from Earth's gravity at the surface of the Earth at 1 meter. And so we have 1 × 10⁻16 at 1 meter, and the accuracy of the best cesium fountain clocks is also at about the same level. So this is a challenging experiment to do, you know, at the meter scale in the lab with existing microwave clocks. But of course, as you all know, there's a new emerging, you know, kind of clock, the optical clock, where we increase the frequency of the transition that we measure with from these microwave frequencies of 10 to the 10 hertz to hundreds of terahertz. And there was a beautiful experiment from the NIST trapped ion group in 2010, where they lifted one clock with a single ion up just a foot with respect to the other clock by actually physically lifting the optical table up with jacks. And we're able to observe this gravitational redshift from that height difference. Since then, there's been more progress. So just a few years ago in Andrew Ludlow's group, they did a comparison between two ytterbium optical lattice clocks, where they did this comparison blind. And they had a height difference between these clocks at 4 centimeters. And this comparison they did at a level of you know, precision and accuracy, where if they had not accounted for the redshift, this comparison would not have agreed, right? So they actually also, in the process of doing this experiment, sort of tested the redshift, although they didn't quite frame it this way, at the sort of centimeter scale with these clocks, which is really, truly amazing. So we've now, as June told us, reached this new era of 10 to the minus 18 or even sub times 10 to the minus 18 accuracy and precision of these clocks. And that is both a challenge and kind of an opportunity. It's a challenge because now it means if we want to compare these clocks across different institutions, we need to know the relative heights of each of those clocks at the centimeter level with respect to Earth's gravitational potential, which is a really hard problem and is very difficult to do. But at the same time, that means that if we've calibrated these clocks and if we trust their accuracy and precision at the level that we say we can measure it, then now we can actually use these clocks as a tool to measure Earth's gravity and Earth's, you know, and the relative heights with respect to Earth's gravitational potential of different locations on the planet, and that has motivated this new emerging application of relativistic geodasy. And so I think that's also an exciting and interesting reason to sort of measure these effects at these millimeter and centimeter scales, because that's exactly the level where now these clocks start to outperform other ways of doing geodasy. So this is really the area that I think I'm going to be telling you about today, and that we already heard a bit about from June. And as I said, one of the other motivations for being in this regime is to start to probe how quantum mechanics and gravity interact. June already showed a version of this kind of experiment, already talked a little bit about this, but there were these nice theory proposals from Zich and Pekovsky et al. Pointing out that suppose you take one of these clock systems, you take an atom and you put it in a superposition of two clock states, and you also put it in a spatial superposition of being at two different heights. Well, now that clock kind of gets some kind of width path information from the gravitational redshift. And so if you do an atom interferometer type experiment where you take this one clock that's already in an internal superposition, put it in a spatial superposition, and then try to interfere it again with this beam splitter up here at the top, you can see that the visibility of the interference fringes for the matter wave will kind of collapse and revive, and that the visibility will depend on this difference due to the redshift. And so this is kind of a first prediction of seeing some kind of interaction between quantum mechanics and a basic effect of general relativity. And this is also, you know, a direction where, as we heard from June, we can start to push in this direction, because we can actually start to both make clocks that are sensitive to the redshift and also sort of make superpositions at this scale. Okay, so with all that as motivation, we built a strontium optical lattice clock to do these kinds of experiments. June already talked a lot about strontium, and so I'm not going to go into it in detail, but, you know, of course, we're using strontium-87. This is our clock transition. We have this amazing, remarkable resource that nature has given us, which is this clock transition with a quality factor of 10 to the 18, and that's really what enables these measurements. Okay, and so we built this, and we don't have access to the same amazing local oscillators that June has spent so much time, June and PTB have really pioneered and spent so much time working on. Instead, we purchased a commercial system, this nice rack-mounted turnkey system, and we managed to trap atoms in our magic wavelength optical lattice. We have this beautiful 1 millihertz line width, and when we do Ramsey spectroscopy on this, we turn out that we're not limited, unfortunately, by that really narrow line width. Instead, we're, of course, limited by the line width of this local oscillator, or by the coherence time of this local oscillator. And so if we do a Ramsey experiment, we end up finding that we have a T2 star time of about 100 milliseconds, which is actually not too bad. I mean, that's pretty good for an optical transition. And so we can sort of naively say, what kind of clock stability do we achieve with this? And it's something like 4 times 10 to the minus 16 per square root hertz if you use the equation that I already showed you. That's also pretty good. I mean, that's not bad for a clock. But then it turns out that no, in fact, that's not true. We haven't taken into account an unfortunate thing known as the Dick effect, which is that we have to spend some amount of time not measuring the local oscillator. We spend some time reloading and retrapping and cooling our atoms. And then as a result, you can confuse high frequency noise for low frequency noise. You get this kind of aliasing of the noise. The expression for the stability of the clock is much messier, but you can kind of simplify it to just being sort of proportional to the stability now of your local oscillator. And in fact, our stability of our clock, which we've now measured, I used to give talks like this before we'd actually done any kind of true clock measurements, but we've now measured the stability of our clock, and it's 6 times 10 to the minus 15 per square root hertz, which is still not bad. I have to say, I mean, you know, for a clock, I'm still, that's not bad. But if you say, all right, well, I've motivated all this by trying to measure the redshift at a millimeter, how long will it take me to measure that with the stability? Then the answer doesn't look so good, right? So at that stability, it would take you 114 years of averaging to average down to 10 to the minus 19. And that's just to measure 1 point, or to measure to see the effect with a standard deviation of 1, and without accounting for any systematics. And of course, you all know that when you do these kind of precision measurements, you spend much, much more time characterizing all of your systematics than you do actually measuring the thing that you're interested in. And so this is just a complete non-starter, right? And so the question is, what can we do about it? Well, what we do is we take inspiration from other experiments that people do, and in particular, you can look at the work done in the atom interferometry community on gravity gradiometry and also measuring of the fine structure constant, for example. Or you can take a look at LIGO, and what they do is they do differential style measurements where they, in the case of the atom interferometers, they split their atom interferometer in two, and they kind of compare the phases accumulated by these two different interferometers. Or in the case of LIGO, you take your laser, and instead of just trying to measure the length of a single arm and being totally limited by your laser frequency noise, you split it in two, and you do a differential comparison where your laser frequency noise drops out. And the same idea here with these atom interferometry experiments, you can cancel out sensitivity to acceleration noise, right? And so we're going to do exactly the same thing. I'll say that we are not the only groups to take this approach of what's known as either correlated noise spectroscopy or differential clock comparisons. June told us about some really nice experiments that were done by Ed Marty and his group, and then subsequently, as we'll talk about with his new extended cavity lattice clock. The trapped ion group has done great work on this. Murray Barrett's group has done work on this at Singapore. Anyway, there's lots of other work on taking advantage of this approach. And so the idea is that we're going to load not just one clock, but multiple clocks into our single apparatus, into our optical lattice here, inside of a single vacuum chamber and inside of the same 1D optical lattice. And we're going to do differential comparisons between them. This is what that actually looks like. So these are actual camera images from our experiment. What we do is we load a single region of the lattice as a standing wave. Then we convert the standing wave into a running wave, and we move the atoms over. Then we load another region, and then at some point we turn the mod off and we shift back so that we have these two clocks now that are spatially resolved and that we can independently read out. And so now we can get really ambitious. We can say, well, I had a coherence time of 100 milliseconds. What happens if I do a Ramsey experiment for 8 seconds? And as you would expect, if you look at a phase acquired by a single ensemble probing for way beyond the laser coherence time, you just get total noise, right? But if we probe with two ensembles at the same time, the two ensembles are experiencing exactly the same laser noise at the same time. And so the noise is kind of completely correlated. It's hard to tell when you plot it like this. So June already showed us these parametric plots or Lissajous type plots where you plot it with the excitation fraction of one region on the x-axis and the excitation fraction of the other region on the y-axis, and you get these beautiful ellipses. And you can see now, kind of make sense of what's happening. We're just randomly sampling two Ramsey fringes that are offset in phase, and that always gives you an ellipse. And if you fit to this ellipse, you can learn very precisely about the phase difference between those two sine waves without being at all limited by the coherence time of your local oscillator. And so this allows us to go from 100 millisecond coherence time to 26-second coherence time. And we've since improved on this. June also showed some really nice data with coherence out to 50 seconds or something like that. We've seen now also coherence times even approaching 70 seconds, something like that. And one interesting question you can ask is what ultimately limits this? And of course, what limits this number turns out to be the Raman scattering from the lattice laser. So by going to these much lower depths, we can push this out. But eventually, this is going to be limited by the lifetime of our clock transition. And so we've been trying in my group to measure that and directly observe radiative decay. I have to say this is totally preliminary and unpublished data. But what we're doing here is we prepare atoms in the excited state inside of our lattice at different depths. And then we monitor the ground state population repeatedly. So we just keep measuring the ground state population as atoms fall down. We image them and then image them again and image them again and image them again as they fall down. And we do that for different depths. And we do it for both strontium 88 and 87. And you can see the curves that we measure as a function of depth for 88 and 87. And you can see the offset between them is really the radiative lifetime of this transition. And so in the end, here at least this is preliminary again, but we measure a lifetime after accounting for also some effects of black body radiation of 120 seconds, which is actually very consistent with the very nice measurements that James Thompson's group did on this by measuring the dipole moment by putting these atoms in a cavity. So anyway, we're still working on trying to push these error bars down a bit more, I have to say. But we do directly see radiative decay on the strontium transition, and this is what's going to ultimately limit the coherence times of these kind of measurements to something like, as June said, 120 seconds or so. Okay, so now we can take advantage of that very long coherence time to make very high precision differential measurements between these clouds. So here in this first paper that June already alluded to, we achieve a stability below 1 × 10⁻17 per root hertz, and we're able to average down into the high 10⁻20s after only 10⁴ seconds of averaging. June told you about some of his beautiful measurements on comparing two halves of an extended cloud, and he got even better stabilities. One point I do want to make, of course, is that those measurements were done with this really, really nice local oscillator, and what I'm showing you here is that actually for these particular style of experiments, it doesn't really matter. So we have a local oscillator that's 2 orders of magnitude worse, and we can still achieve basically the same stabilities. We've since continued to improve our stability, so we're now at about the same level that June is able to achieve. And actually what's limiting this, we're really at the QPN limit. So what's limiting this is just how many atoms we can really put in there without starting to be limited by density effects. And June has this very nice in-vacuum buildup cavity that lets him have a bigger beam waist, and so he has more, many more atoms and achieves a higher stability. But this is not limited by.
Told them my patient listen to them and said, you know, it is in your hands. You can change.
I don't know if somebody.
Start coming to me.
Okay, so I'll just keep going. Anyway. Okay, so now just to remind you, we had this situation where we were at a stability of 6 times 10 to the minus 15 per root Hertz, and it would take us 114 years to average down to the redshift at a millimeter. We're now, with our new stabilities that we achieve, able to average down to 10 to the minus 19 after only an hour and a half. And so now this starts to become a kind of achievable experiment to measure the redshift at the millimeter scale. I do want to make the connection back to the Pound-Rebka experiment, because I sort of complained that one of the issues with the Pound-Rebka experiment is you have no idea what the frequency of the Mossbauer or radiation is. And of course, now we're in the same position again. By doing these differential comparisons, we've canceled out what the clock laser is doing, so we have no idea what the clock laser frequency is here. But we're able to still measure the sort of the frequency difference between these clouds. However, we can do a trick that I think would be very difficult with Mossbauer spectroscopy. We don't have to load just 2 regions of our lattice. We can load as many regions as we'd like. And so here this is showing you a movie where we load 6 regions of the lattice to kind of make 6 clocks. And this makes a sort of miniature clock network. So here I'm showing now 5 regions. We can load it however many we want, really. And if you do this measurement with 5 regions, you get simultaneously 10 unique pairwise comparisons between these different regions. And so we get 10 of these ellipses simultaneously. And as a result, we can learn about the redshift at a bunch of different heights at the same time, right? So we're able to measure the redshift at 1 centimeter, 5 millimeters, 2.5 millimeters, all simultaneously. In addition, I think there's a lot of promising future applications of this approach that I'm kind of showing very quickly here, and then I'm happy to talk about later in the discussion period if you'd like, but I'm going to focus right now on these redshift measurements. So as I said, we're measuring at 1 centimeter, and we should be able to see that after only 2 minutes of averaging. We're also measuring at 2.5 millimeters, and we're doing 4 different measurements of the frequency difference between clocks separated by 2.5 millimeters all at the same time. But again, these averaging times just refer to what you need to get to the precision or the statistical uncertainty to see the redshift. Of course, you have to account for all of the systematics in this system as well. So there are a bunch of other things that in principle could mimic a redshift or mask a redshift. And most of those things in our system, essentially almost all of them are some form of gradient, because now we're looking at frequency differences between these clouds. So gradients in magnetic fields or gradients in temperature or gradients in electric fields can all give you clock shifts between these different ensembles. And we won't be able to necessarily tell the difference between those and the redshift. We characterized all of these, and I want to say we did it blind so that we weren't biased in whether or not we got the result that we expected. And so here you can see the value that we were actually measuring for this fractional frequency gradient after subtracting all of the systematic effects that we characterized off. And you can see the possible range of values that the blind could have taken that we added in software. And you can see the actual expected redshift down here is the black line. So we didn't know when we were measuring whether this was consistent or not. And I'm happy to say that after removing the blind, we found, not surprisingly, that as June said, we're not really doubting Einstein here, right? We kind of know that Einstein is right. And indeed, we are able to observe the gravitational redshift across this 1 centimeter array of clocks. Here's our sort of systematic uncertainty. All of the contributions to it. So we're actually characterizing the differentials in all of these effects at the 10 to the minus 19 level. And one other comment I want to make, sort of motivating this work and about its potential impacts, is that of course some of these gradients are going to start to matter for absolute clock accuracy as well. At some point, you're going to have to start worrying about the magnetic field gradients and electric field gradients and everything like that in these clocks, and not just about the kind of average value at the center of the cloud. And so I think this kind of technique is an easy way to at least start to characterize those for absolute clock, characterizations as well. But my favorite way of visualizing our results is this. So this is now plotting our average values for the frequency differences after subtracting all of our systematic effects off as a function of height difference. And so here you're actually visibly seeing the redshift, gravitational redshift showing up across this array of clocks. over a height difference of just 1 centimeter. And again, I think this bodes really well for ultimately being able to make similar measurements using relativistic geodasy. Although, of course, we're cheating here, right? We're doing everything in the same environment with the same clock laser. It's going to be much more challenging to do differential measurements across longer baselines where you have phase noise that shows up along the fiber link or in free space, and where your atoms are in totally different environments. And so you need to characterize each of them at the level that we're getting from doing these differential comparisons. But nevertheless, I just want to emphasize that we're actually, our minimum, as June said now, our minimum sensitivity from these measurements was at the level of about 1 millimeter to the redshift. And that's sort of, less than the thickness of a penny. So to me, it's pretty amazing to think that we can now see the redshift at these scales. You can also view this as a test of relativity. Great, thanks, Ana Maria. You can view this as sort of, a test of local position invariance. And you can compare this number actually, and it's quite similar to the number that, Pound wrote in his notebook when he was analyzing his data. This is that, there's a nice article from the Harvard Physics Newsletter where they actually showed the original notebook from Pound's experiments, and he kind of put this nice box, just like an undergraduate lab experiment or something, around his result. You can see that we're actually pretty similar. So we can visualize where we're at compared to Pound and Rebkin. We're basically almost at the same level here. And of course, you also see June's experiment up here, where June was able to measure it at even a smaller length scale, sort of sub-millimeter scales. Really beautiful, remarkable, result. And we can sort of say, well, where do we go from here? So one thing I want to say is actually, if you look at the history, Pound and Rebka were able to improve their constraints as a test of relativity by about a factor of 10 in 5 years. And I actually think it's quite reasonable for us to do something similar. I think we can characterize these gradients. We've learned a lot from doing this initial experiment. This was just our first attempt at this. I think it's quite reasonable to think that we can characterize these gradients at a similar level and get something like a factor of 10 improvement in our current apparatus. But if you want to get really crazy and ambitious, and I think this will be very challenging, you could imagine doing a meter scale type experiment and also still achieving that extra factor of 10 improvement in uncertainty. And then you're really pushing up against the constraints that people are putting with space-based experiments. So this is gravity probe A here, and this is this Galileo, satellite that was accidentally put into an elliptical orbit down here. And I think we could actually in the lab put kind of competitive limits on limits to the local position, modifications to local position invariance. And one motivation for that is coming back to this experiment I told you about. If you imagine trying to put one of these strontium atoms that's in a clock superposition into a spatial superposition, you can say, okay, well, you can measure the redshift now, and people do atom interferometry, including some of the people in the audience do atom interferometry with strontium. So why not just do your experiment and see if you can see these changes in visibility? And if you imagine doing that with a centimeter change and waiting 10 seconds, which is a long time, but it's how long we're kind of interrogating our clock when we're not in a spatial superposition. At a 1 centimeter height difference and 10 seconds long, the actual phase difference is only 27 milliradians that's accumulated between these two clouds. So the only reason that we're actually able to see this is because we're averaging down a very, very small phase difference between these two ensembles. And that means that from the perspective of sort of nature or quantum mechanics, they're pretty much in the same state. When you recombine them in this experiment, the visibility of the fringe would still be 0.9999, right? Because they're essentially, at least if you're only considering the redshift, they're still in the same state. And so you're not really going to see any collapse in the fringe. So in order to see that, you need something more like a difference of a meter and 11 seconds, and then that gives you exactly pi radians of phase difference. And so that also motivates, a larger scale experiment. I'm very happy to say that I'm part of a proposal. I was lucky enough to be on a proposal with our session chair, Ana Maria, and previous speaker, June, and also Igor Pekovsky, who's speaking later in the session, later in this conference, I think on Tuesday or Wednesday. And we've received funding from both the Sloan Foundation and the Simons Foundation, and the whole thing was organized by the Moore Foundation to actually pursue some of these experiments in this direction, and also to do some other experiments that June told you about involving these Wannier-Stark states, and some interesting new tests of the equivalence principle that I'm, again, happy to talk about during the discussion section. But the last thing I want to say in my remaining 2 minutes or something is you can imagine what if we got the level of precision that we're currently getting here, up here in the lab at only height differences of 10 to the minus 3 meters, but with height differences of, millions of meters, right? And of course, that's what you get if you put these clocks in space. And then you could get, many orders of magnitude improvement on constraints on, modifications to relativity. And that is, of course, the motivation for, or one of the motivations for putting optical clocks in space. I'm showing just one example of some of the proposals people have put out there for putting these optical clocks in space. And there's this meeting tomorrow that I'm very much looking forward to of the FunPag group, where I think this is really should be one of the main things that we really are working towards and pushing towards. And in that spirit, a lot of the tricks that we're using in this lab-based measurement aren't going to work for clocks in space. And so I think it's also important to think about, what can you do when you are truly limited by this local oscillator noise because you can't necessarily do these differential comparisons and things like that. And in my own group, we've done some recent work that was also inspired by some work done by other members of the audience, by Smerzi and Petze, on how you can improve these clocks, their absolute precision, not the differential precision in clock comparisons, by also taking advantage of having multiple ensembles. So in this case, we used this scheme where we have two ensembles and they're 90 degrees out of phase from each other. And this actually allows you for the same local oscillator to double the coherent interrogation time, basically for free, and to get a square root of 2 enhancement and stability. And we showed that that works basically exactly as you would expect. And then we were able, by using multiple ensembles and a magnetic field gradient and some tricks, to actually get 4 ensembles that we had somewhat independent control over so that we could start to do some versions of phase estimation algorithms and push past, just being limited by the coherent interrogation time set by your local oscillator, but kind of keep following the phase past 2 pi, if you want to think about it that way. And so this is work that's on the archive right now, and I think it's quite promising, and I actually have a collaboration with some of the other members of the audience, including Mariana and Andrew Jayich, on sort of trying to push this even further and explore new ways to kind of use these more sophisticated measurement algorithms to maybe get more performance out of the same, say, set of resources that you have, the same atom number, the same local oscillator. And maybe the one thing I'll say is that I think while spin squeezing is the ultimate thing that you need to do once you've really achieved the quantum projection noise limit and you've squeezed everything out of the resources that you have, I don't think we're at that point yet for these clocks. As we heard from June, there's A, still opportunity to put more atoms in, but B, for a given number of atoms, there's more efficient ways to use that number of atoms than what we're doing right now by just probing them all for the same amount of time and with the same Ramsey sequence. Another kind of thing I'll just make a quick plug for is that there's a lot of really exciting ideas coming out of quantum computing. And regardless of what you think about, kind of the prospects for quantum computing or whatever, I think one really nice thing about it is it leads to new understanding and new ideas and new proposals for all kinds of new ideas with these systems. And motivated by some of the ideas in error correction, there's this idea of what are called using erasure errors and erasure conversion to reduce the requirements on gate fidelities and the number of qubits that you need to achieve fault tolerance and things like that. And we're implementing some of these same ideas in our clock measurements. So we have this collaboration with Alexei Gorshkov and Michael Gullins and Jeff Thompson, kind of showing how to understand when you have a depolarization or poly error versus when you have an erasure error, how that impacts the stability of your clock. This is also on the archive just as of last week. And we've actually done some very preliminary measurements in our lab showing that indeed, if you kind of are more careful about how you do your measurements and convert some of your errors into erasures, you can actually increase the coherent interrogation time and, in principle, the stability of your clock. Okay, so with that, I want to thank all of the students and postdocs in my group who did this work, and in particular, I want to highlight Dr. Xin Zhang, who really built this experiment with me and really pushed this forward, as well as grad student Jack Doldy, who's now moved with me from Wisconsin to Berkeley, and I'll thank you for your attention.
Thank you, Shimon, for the very, very nice talk. So we are open for questions.
So thank you for a very nice talk. You mentioned the meter scale lattice experiment. How would it look like? Are we still talking about the same environment, or are we talking about really separate environments separated by a meter?
Yeah, thanks. So what I'm envisioning is still a single vacuum chamber, sort of inspired by what people are doing in the atom interferometry community. So sort of an extended chamber, and what I'm envisioning actually is still a single 1D lattice with a very large beam waist and a long Rayleigh range, and a very low depth lattice, because we now know that we can get away with that. You know, having multiple zones in that very extended sort of meter scale 1D lattice, where we can do comparisons between them. We can move our atoms up and down and shift them around. That's the idea. It doesn't exist yet. It's still in the design phase, but it's part of the plan for what I'm sort of going to be building up at Berkeley now that we're.
Thank you.
Yes, let me first ask one question, Shimon. So how are you dealing with the density shifts? And for example, you mentioned comparison between 88 and 87, then you will have to deal with a...
Yeah, okay, so specifically, the one part where I showed the comparison between 88 and 87, that was not a clock comparison, that was just looking at lifetimes. And there we just, in those measurements, we actually try to just keep the density fairly low, so that, because there is two-body loss, of course, and that's also something that we have to account for in those measurements. But we actually do is the same standard thing of making the lever arm kind of big by loading at high density and low density, and kind of making sure we understand the rates in those two different cases. But we try to mostly just stay to low enough densities where the density shifts don't matter. In the case of the redshift measurements, we characterized our uncertainty. So we basically would intentionally load very large differences in the number of atoms between different sites and characterize the shift, and it scales the way that it always does in these 1D lattices. And then we measured how many atoms we had in each shot, basically, so that we knew, you know, what our uncertainty and the density in each region was, and that's what ended up giving us our systematic uncertainty. But we actually, shot by shot, like in each measurement, we subtracted off what we believed the density shift to be, and then we know what our uncertainty in that is. But we mostly just try to stay at low enough densities that it doesn't limit our coherence time, and then we characterize what the residual sort of shift of the frequency actually is. But I think the right way to deal with it is either move to a 3D or 2D geometry, or move to a much, much bigger beam waist, and June has demonstrated that by using a cavity, a build-up cavity, you can achieve the same lattice depths with a larger beam waist and have less density shifts for the same number of atoms. And then actually what's nice, that what we've learned from these experiments and what June has also showed, is that we actually want to be, at least on Earth, when we have Earth's gravity helping hold our atoms in place, we want to be in very shallow lattices anyway for these kind of differential comparisons, and I think even for absolute clocks. So so that's handy, because that also means you can get away with a bigger beam waist and more atoms.
And you're using mostly Rabi spectroscopy or Ramsey?
No, we use exclusively pretty much Ramsey, and that's a result of our clock. So our clock laser is just not very nice, and so we can't do the seconds long interrogations that June does on Rabi, which are very nice. So we unfortunately don't have as easy of a way, for example, to get the cancellation of density shifts from the S wave, P wave effects that you so nicely showed. But I mean, I guess there's something equivalent one could do with asymmetric excitation fraction or something like that, but we haven't explored that yet. It would be great to discuss.
Great.
Yeah, it's great to see these conveyor belt movies. I'm curious about like motional excitation as you separate the sample. Is this not an issue at all, or do you basically have to recool the samples after separation?
So what's interesting, actually, if you watch those videos, you can see some of the hotter atoms fly away each time here. So if we, each time we stop, you can see a little puff of atoms that keeps going. So the hotter atoms do get carried away, but we find that it's almost a form of like evaporative cooling or something, where the atoms that remain are actually colder than before we did the move, because the hotter ones just left. We can cool after the fact, but I think, so we do some amount of Z, cooling along the lattice axis we do after we're done with the move. But actually we find that the temperature before the move and after the move is actually colder after, because the hotter atoms are gone.
But at this point, the sample is already spin polarized, I assume?
No, I don't believe so. I think we do the spin polarization afterwards, although I have Yeah, no, for sure, because the mod is still on here. So we do spin polarization and some in lattice cooling after the move.
I see. So it's not just the hotter ones fly away. There's some thermalization.
Yes, and there's some thermalization. Yes, that's right.
More questions?
Some years ago, there was a somehow controversial paper on measuring the gravitational redshift with atom interferometry. Since you are now in Berkeley, did you have the chance to discuss with Holger Mueller about the relation? Because then, especially here, things get very close, no? When you show the interferometer with strontium, also experimentally.
Yeah, so that's a good question. I have chatted a bit with Holger about it. I should chat with him more about it. My understanding is that I think the current agreed upon understanding is you can't view that as a general test of the redshift. It tests specific modifications to it that are not as general as when we write down just local position invariance. This is how I understand it, at least. And I think that Holger agrees with that. So that's why we don't put these, atom interferometer limits on these plots. Otherwise, they would be well below all of the existing plots. But I think those are just not as general, I would say, as those only test very specific modifications that I think some people would claim are not well motivated. But that's my understanding.
It's easier here, and we will have both.
Just as a comment, I think that, Shimon, as you pointed out, it's probably the internal degrees of freedom, the delta E really matters. In traditional atom interferometer, the delta E is between hyperfine states. And so in order to really test the general relativity, I think this mass defect effect is actually, in fact, tremendously important. So I would argue the traditional atom interferometer experiments really is just measuring the action of gravity, but not at redshift.
So in your clock network with the multiple ensemble, you show differential comparison between nearest. Okay.
Between all of them, actually, yeah. So.
And what about a multi-dimensional?
Well, yeah. So we right now only have a 1D lattice.
No, but a comparison, I don't know, between the first, the second, and the third at the same time.
Yes. Okay, that's a great question. I mean, we have sort of thought about that, and in fact, so one trick that we use to make sure that we're doing everything properly is to draw kind of loops, right? So. You can look at the frequency difference, between clock 1 and clock 2, but you can also look at the difference between 2 and 3 and 3 and 1, and always make sure that your loop subtracts to 0, because the frequency difference around any closed loop has to be 0. And that was one way that we sanity checked our results and actually found a kind of technical issue that we had in our experiment, where when we were first measuring, we would probe for too long, and some of the atoms from cloud 5 would end up in the region that we called cloud 4 because they got kicked out and we were still imaging. And so we had these funny correlations between sites that we were able to figure out by measuring around these closed loops. We are not right now doing any kind of more sophisticated like third order correlation measurement, but we can do it. I mean, we have all of the data and it's just how you process it after the fact. And I think that's a really interesting question. And in fact, in some of my other research with NV centers, we were actually trying to do some of those kinds of third order correlation measurements, but I'd love to discuss more if there's something specific that would be interesting to look at. Yeah.
Thank you. Thank you.
Last question.
It's not a question, it's rather a comment about redshift effects in atom interferometers. I think what is agreed upon now is that if you would like to probe that with an atom interferometer, you need 2 states on each of the paths. This is what people call quantum clock experiments. Yeah. You can do them also with atom interferometers. That's actually the idea, to do them in Hanover, for example, in the 10-meter fountain with ytterbium.
Yes.
So there were like works by the groups in Ulm and in Hanover to show that this is where you have access to general relativity effects. Actually, the proposal by Magdalena Züsch and others is only able to resolve special relativity effects. Well,
I'm not sure I understand that last statement, but maybe we can discuss that offline. But But I do agree 100% with that. And of course, it's not to say that atom interferometers can't measure these, but rather that the traditional ones, as June said, with hyperfine states or where they're actually in the same, internal state, those are probably not, sensitive to the redshift.
Great. So we have a very nice session. So let's thank June and Shimon one more time. And we have a break and we will be back at 11.